Hello everyone and welcome back. My name is Mr. Cobalt, and in this video I'm going to be going over how to calculate the delta S for a change in state. So I'm going to go over a couple of practice problems. So let's get into this. So first of all, we're going to be using this equation up here. So delta S is equal to the Q value of a reversible process divided by the temperature. Remember, temperature in this case should be in Kelvin. And then also the Q that we're referring to, the Q reversible, that is the heat of a reversible process, the heat that's either being absorbed or gained during a reversible process. And so a reversible process is something where you have the forward and backward reactions that are happening at the same time, right? So under specific conditions, that's going to occur. So I'll talk about that during the problems that I'm working out. So let's get into this. So in this problem here, I have 25.0 grams of water and it condenses at 100 degrees Celsius. Now you're probably thinking, wait a minute, water condensing at 100 degrees Celsius? Doesn't water boil at 100 degrees Celsius? Well, that is true too. The truth is that both processes happen at 100 degrees. So it just depends on which direction you're going, right? So if I have a superheated like gas of water, water vapor, maybe at 120 degrees, and I start to cool it down, at 100 degrees is when the condensation process starts to begin. Or I could have water, liquid water, at 90 degrees, and I could be raising the temperature to 100 degrees, and then at 100 degrees it would start to boil and vaporize. The truth is, at 100 degrees, if we have water at 100 degrees, both processes are happening at the same time. The condensation process and the vaporization process are happening simultaneously. So both processes happen at 100 degrees. So here we're focused on condensing. So the water condenses at 100 degrees. So because we're at exactly 100 degrees Celsius, both processes are happening at the same time, and therefore we have a reversible process. If we had a slightly lower temperature or a slightly higher temperature, only one process would be happening. So either the water would completely, condense, and there would be no reversible, like it's not going to become vapor again, right? So if it's at 99 degrees Celsius, the water is going to all, if it's gas, it's going to all condense and stay as a liquid. It's not going to, none of the liquid is going to come out of solution or is going to vaporize at that temperature. So, but if it's higher than 100 degrees, so if it's 101 degrees, then the water is going to boil off and you're going to lose all your water eventually. So let's go ahead and do this problem. So here we have 25 degrees Celsius, 25.0 grams of water. We need these two. We need these two things to calculate the delta S. We need the heat of the reversible reaction that's happening during this process, and then we need the temperature. So they gave us the temperature. We need to convert that to Kelvin. So we're gonna take 100 degrees Celsius, we're going to add 273.15 to that, and we get 373.15 Kelvin. So there's our temperature in Kelvin. Now we need to calculate the Q of the reversible action, the heat of the reversible process. So in this case, we're going to need to figure out, we're going to have to look up the heat of vaporization or the heat of condensation. So remember, at the process at 100 degrees, water can boil or it can condense. So in order to figure out how much heat is absorbed during that process, we need to know how much heat is absorbed during condensation or during boiling per certain amount of the material, per mole or per gram or whatever it is. So usually it's going to be like kilojoules per mole or joules per mole. And so we got to look that up. So we're going to look up, since we're condensing water, we need to look up the condensation, the heat of condensation. But most likely what we're going to find is the heat of vaporization. But the thing to remember is that since vaporization and condensation are opposites of each other, they're opposite processes. That means that the heat of vaporization and the heat of condensation are going to be the same value, but just different different signs. So one's going to be positive, one's going to be negative. So if we look up the heat of vaporization, so we got, that's going to be our delta H of vaporization, VAP. We looked that up and it is 40.7. So that's equal to 40.7 kilojoules per mole. Let me double check that. Yep, 40.7 kilojoules per mole. So this is the amount of energy that is absorbed during the vaporization process. So in order to vaporize 1 mole of water, you need to add 40.7 kilojoules of energy. So now we can take this and help us convert this into the amount of energy that would be absorbed or released by that amount of water. In this case, since we're condensing it, this is positive here. Vaporization is positive because we're adding energy to vaporize the water. But in our problem, we're condensing it. So in that case, the water is losing energy. And since it's losing energy, it should be negative, right? So then that's going to be the delta H of condensation. I'll just put that for the delta H of condensation, which is the opposite of the heat of vaporization. So this is going to be a negative 40.7 kilojoules per mole. Okay, so we have our delta H of condensation, the heat of condensation. So we can use this to help us calculate, convert this 25 grams into energy. So we're going to go ahead and do that. So we start with our 25.0 grams of water, H2O, put that over 1. We're going to have to convert this to moles. If we're going to use this conversion factor of moles and kilojoules, we're going to convert this to moles. So we know that from the periodic table, you calculate the molar mass. The molar mass is going to be, for water, 18.016 grams of water is equal to 1 mole of water. So grams cancels out. And now I can use my conversion factor here. I know that for every mole of water, I need 40.7 kilojoules to be released. Negative. The water is the system. It's losing energy. It's going to be negative. So then I put 1 mole of water here. And then the negative 40.7 kilojoules goes on top. So the moles of water cancel out. Now I have kilojoules. So I calculate that out. And when I do, I get, let's see here. I get, one more step, forgot. So before we do that, we need to calculate this in joules. So remember, it's important to remember the units of your delta S. Delta S is in joules per Kelvin. So we need to convert this to joules. So we're not done yet. We need one more step. So we're going to have to convert kilojoules to joules. So here we have 1 kilojoule. And then that's going to be equal to 1,000 joules of energy. So we convert that to joules. Now we can do our calculation. And then when we do that, we get, 5.647. So this is going to be equal to 5.467 times 10 to the 4 joules. Just let me double check that I did that right for 5 point. And don't forget that this is negative because this is negative here. So this is the amount of energy in joules that was released during the condensation process of 25 degrees or 25 grams of water at 100 degrees Celsius. So now I have the joules, which is our Q. I have the temperature. So now using this equation, I just divide the two. So then delta S is going to be equal to negative 5.467 times 10 to the 4 joules divided by our temperature, 373.15 Kelvin. And I divide that, and I get, what answer did I get? Negative 151 point, do I have a point there? Nope. 151 joules per Kelvin. Let me double check that. No, I found a mistake. So I transpose these numbers, so it should be 647. Sorry about that. 647. Let me double check. Okay, so then 647 divided by that, and I get 151 joules, negative 151 joules. So here is the change in delta S of that process. All right, let's go ahead and do this one. Here we have 10.0 grams of acetone, and here's the formula for acetone, and that's going to be vaporized at 56.1 degrees Celsius. So again, we're going to find the Q of the reversible divided by the temperature. So temperature they're giving us is 56.1 degrees Celsius. We're going to add 273.15, and that gives us, what did I calculate that to be? That's going to be 329.25. Yes, that's right, 25 Kelvin. So now I have the temperature. So now I just need to find the heat of the reversible process. In this case, we are vaporizing at 56.1 degrees, which is, again, the boiling point of acetone, right? So here, we're going to start with 100 grams. If we look, we got to look up the heat of vaporization. And when we look that up, again, the heat of vaporization is 29.1 kilojoules per mole. So delta H of vaporization is equal to, what did I say it was, 29.1? So 29.1 kilojoules per mole. So now I'm going to take my 10 grams. So I do my conversion, 10.0 grams of my acetone C3H6O over 1. I'm going to multiply that by its molar mass. So you calculate the molar mass of acetone. And when you do that, you get 58.081. So we have 58 point, what did I say, 0.081 grams of the acetone C3H6O over 1 mole of the C3H6O, the acetone. So grams of the acetone cancel out. Now I have moles. Now I'm going to use the heat of vaporization to convert to kilojoules. So I'm going to convert that to kilojoules. So 1 mole of the C3H6O, and then I have the 29.1. So 29.1 kilojoules. And then finally, I want to convert kilojoules to joules. So 1 kilojoule over 1,000 joules. So now kilojoules cancels out. Oops, I forgot here. Moles of my acetone cancel out there. So now I have joules. So now I can calculate the amount of joules from this process of vaporizing 10 grams of acetone. And that came out to be 5.01 times 10 to the third. Oops, I should write that better. Third joules. And you can see here, because this is positive, heat of vaporization is positive because you're putting energy in. Energy is being absorbed by the system. So that's a positive value. It's absorbing, it's gaining energy. And so therefore we end up with an energy that is positive. So now all we need to do is, again, plug it into our equation. So we take the amount of energy in joules. So we take 5.01 times 10 to the third joules. Divide that by our temperature. That's going to be 329.25 Kelvin. And that will give us a 15.2 joules per Kelvin. So that is the change in entropy when we take 10 grams of acetone and vaporize it at 56.1 degrees Celsius. So I hope this is helpful. If you found this video interesting, if this was helpful in any way, if you learned anything, then please, by all means, like the video, share it with your friends, hit that like button over there somewhere. Also, subscribe to my channel. Make sure you hit that notification bell, and when you do, click all so you can be notified by all the videos I put out. And then finally, put a comment down below. Let me know what you think. Ask me questions, make suggestions. I would love to hear from you. Thanks for joining me, and have a great day.